panel focuses on materials industry. We have 4 panelists and a moderator. Let me introduce them. From JSR Corporation, we have Yuya Ohnishi, and from Panasonic Holdings, Takahiro Ohgoe, and Mitsubishi Chemical Corporation, Mr. Chigao, and from ENEOS Corporation, we have Takafumi Ishii as panelists, and Mr. Masaru Tsuchiya will be the moderator. Mr. Tsuchiya, you have the floor.
Thank you very much. I am Tsuchiya from McKinsey and Company. I am associate partner at McKinsey and I'm one of the leaders of advanced electronics, including quantum computing. I temporarily belongs to a quantum computing lab, but I was actually working on semiconductor technology. And back then, I thought a quantum technology is a technology of a very far future, but now it is becoming a near future technology. So my main field is actually hydrogen and battery, but even in those areas, there are high hopes for quantum computing technology. So today's focus is materials, and I feel very familiar with the materials topic today. So if you look at quantum computing from materials perspective, then McKinsey, we always study the future direction of certain technologies. And in terms of quantum and materials, we say that if you have 420 qubits, that will be good enough to generate value. 8.5 trillion to 107 trillion, 85 to 107 trillion yen of value is what we expect for the future. However, this is a very wide range, and materials is the area where we have a lot of expectations. And we expect value generation between $120 billion to $320 billion in this area. At McKinsey, we look at various use cases. For example, the fuel cell will be critical for sustainability, or lithium-ion battery, or the hydrogen reaction, and also the ammonia synthesis is very important. Conventional way is Haber-Bosch, but we do not have a lot of innovation. Or zero-carbon cement, or for a petrochemical area, the molecular structure. Those are many use cases, and we have high hopes in those areas for quantum computing. We have panelists from chemical or electronics as well as a petrochemical. I think we have a great panel to do good discussions. Now, as we start the panel, let's ask each of you to introduce yourself. There are 2 questions. First, what is your current organization and your current job? And how you came to be involved in quantum computing. Ohnishi-san, could you start?
Yes, I am from JSR Corporation, RD Technology Digital Transformation Center, Materials Informatics Promotion Office, and I'm a deputy head of that office. And as you see from this title, my job is to provide latest technology, in particular digital technologies, into R&D to accelerate R&D activities, the so-called materials informatics. I'm leading that effort. So I'm a manager, basically, but when it comes to quantum computing, I used to do some research activities as well. So why I am involved in quantum computing? In 2018, Keio University created an IBM Hubbard Keio University quantum network, and we were one of the 4 founding companies, and I was dispatched as the first researcher. So since 2018, I have been engaged in quantum computing research. Ohgoe-san, please. I am Ohgoe from Panasonic Holdings. I belong to Technology Division Material Application Technology Center, which is a corporate R&D division. Our main job is digital transformation for materials development. I have 2 hats. First is a introducing DX into materials and device development. And we are trying to contribute to an actual product development roadmap. And another role is related to future. Explore new technologies and explore and acquire new technologies for our success in the future. And quantum computing is part of the latter initiative. About 3 years ago, we started to work on quantum computing. My background comes from a quantum simulation and application as a university researcher. So I have some ties with that area. That's why I was brought into this work. Thank you very much. Then Mr. Gao, please. I am Chigao, Mitsubishi Chemical. Science and Innovation Center is my organization. Material Design Laboratory is my direct organization. And my specialty is computation science. And so far, we have analyzed the chemical reaction and materials development using quantum chemical computing, and we used material informatics to develop materials. So how I became involved in quantum computing? Exactly the same as Ohnishi-san from JSR. Back in 2018, IBM Q Hub at Keio University was created and we joined it. And that was the moment I started to work on quantum computing. Until today, I have used quantum computers, quantum AI, or optimization researches we conducted. For example, one example is an OLED light-emitting substance and simulation of performance of such substances, or quantum AI algorithm development. Regarding optimization problem, we published a paper about using the optimization problem in the area of a organic light-emitting substance. I am Ishii from ENEOS Corporation. I belong to MRE Technology Department of the Central Technology Research Center. What I work on is molecular simulation, sometimes combined with machine learning. In our research center, we work on various issues and themes, and I contribute to those researches. And another part is we also contribute to resolve production issues when they arise. I have another mission as well. About 2 years ago, preferred networks, about the neural network, developed neural network potential, and we commercialized it under the name of Matrantics as a service, and we jointly developed that. So a functional enhancement of Matrantis and the business operation for the Matrantis. These are also a part of our mission in our group. Generally speaking, exploring new technologies is of course part of our mission. So in that sense, about 5 years ago, we did a startup pitch. At that time, we organized a startup pitch, and Kinesis applied to that. Back then, I knew nothing about quantum computing, but as I heard Kinesis' pitch, my first impression with Kinesis was great. I thought it's a great company. And also, I felt a huge potential for quantum computing as I heard their pitch. And that is how we started joint research with them. Speaking about myself, my specialty is synthesis. So not an expert in theoretical area. Quantum is something the least thing I want is to be involved. But one is web optics. When a light comes in to a liquid crystal, how the reflection happens. I did that kind of simulation, and then
when I did that, I saw some commonalities with my specialty, and MNR is often used. And spin pulse technique is used to apply 90 degrees pulse and other things. So very vaguely, I was feeling familiarized with quantum technology, or in NMR, if you think about, I'm not an expert of signals, but we calculate the spin Hamiltonian sometimes, and with a very few number of spins, we had to do a lot of calculation. In that sense, I was feeling the large potential of quantum technology. And after decades since then, I am getting involved with quantum computing. Now, that is how I ended up here.
Thank you very much for sharing with us your processes, how you got involved in quantum computing, and you have different backgrounds and came into the field of quantum computing. What kind of problems do you expect to solve? Computational science or the biology or material sciences? You are in different specialty fields. So I'd like to ask you, starting from Kochi-san, material science is your background. What kind of problems would you like to find a solution? Before talking about that, I have to talk about which problems cannot be solved. Using classical computation against the computational size, the cost will exponentially grow. So, for instance, there is a surgical issue, a circulatory issue, and also at the time that the AI machine learning is conducted, there is a dice issue, and also when we try to find a strict solution in quantum science, that's also quite costly. And if we do use the classical computing, we can only handle very small size. But making use of quantum computing, this optimization solution, strict solution, will be able to handle larger size, and that will be leading to the practical application. So far, for instance, metal, the reactions or the physical properties of materials, computations will be able to be processed, making use of quantum computations. For instance, Femoco, there is the metal, and this Femoco, if the mechanism can be elucidated, then we'll be able to create a very good material and we'll be able to make a contribution to achieve carbon neutrality. Thank you very much. So we do have expectations for sustainability. Therefore, I wish that you actually establish a good use case. Ishii-san, how about you? What can be done by quantum computing? I think there are many. But amongst all, what we are interested very much is catalysts. And catalyst in our current business, it is utilized in the oil refinement activities. However, technology-wise, we have almost exhausted the technological advancement. But new area, for instance, how to convert hydrogen in more useful, easy-to-use materials. As we try to achieve a carbon neutral, catalyst is quite important, and this actually gives stimuli to the chemical reaction, and it is rather difficult to make use of computational power in catalyst development. Even if it is very simple chemical reaction, and even if we conduct a high-order DFT computations, the solutions are not necessarily accurate, and we have to consider electron correlations quite deeply, and that goes beyond the power of classical systems, but quantum system may be able to do that. Therefore, that's one of the big expectations. And also within my company, for instance, the tankers wiring distribution optimization, that's the ENEOS space. And also more long-term FTQC is another challenge, but I myself haven't reached to that space, but ENEOS, the others are also tackling. Yes, hydrogen, the platinum or iridium, those catalysts are quite important, and without developing the good catalyst, sustainability cannot be achieved. Therefore, I think that's important challenge. Next, Ohnishi-san, please. Well, I think already two people mentioned what I am going to say. So in classical computing, if computation is difficult, then those could be calculated by quantum computing. And for those who are not specialists of science, if I consider in a more plain term, little unstable substances, those calculations are quite challenging. And if we can make very good use of those little unstable materials, then by inputting a small amount of catalyst, it may lead to a big change. And JSR is involved in highly functional the materials development, especially by shedding light. Function may emerge or generated. So by irradiating the light, the substance excited, becoming a little more unstable. And that is unstable state, and it is difficult to accurately calculate with classical computation. And you may consider, then why not conducting experiments? The reaction is very quick by shedding light. Therefore, it's very difficult to conduct experiments. Therefore, we would like to elucidate what's going on in computation. But using quantum computation, we'll be able to clarify what's happening there, and we'll be able to develop new materials. We'll be able to enhance the performance of the materials. And that way, we would like to use quantum computing. Thank you very much. So resistor is a very important area, and Japan has been champion in this space. So if we can see more innovations, that would be great. Thank you. Ohgoe-san, please. Our company has been handling many different businesses, and crystal-related materials are one of the areas that we need to develop. So in terms of application of quantum computing, I think probably we will start with molecules, but going beyond that, crystals R&D acceleration is the area that we'll be able to also use quantum computing in the future. Currently, regarding crystals, there is a so-called strongly correlated substances. Then the classical algorithms cannot give accurate solution in the first order, but quantum computing can or may be able to overcome that, and in that sense it is a dream technology. And my personal background is that I used to be a college researcher, and I was handling superconducting materials. It is a crystal most challenging problems, and back then we tried our best and came up with the then best solution. However, it's not concluded yet. So in that basic research area, high temperature superconducting materials, those most difficult problems could be solved. Then I think truly the dream will come true. Well, as a researcher, the high temperature superconducting materials, in order to increase the electric wires, that's quite important topic as well. So I wish that you find a good solution. So thank you very much, and I'd like to ask questions. Then after that, if we have spare time, we'd like to open the floor. So you have now briefly shared your use cases. But at this point in time, we haven't seen any breakthrough news, meaning that there are still challenges. What other challenges do you have today? And if there is a big breakthrough to take place, what will be needed for them to happen? Coach-san, could you start? What's your observation? First, regarding the issues or challenges, it's not yet in practical use. One of the major causes is that the current devices are disk devices, and with a qubit performance, there will be big errors generated, and as a result, there is a limitation. And those limited disk devices, in order to make use of those devices, risk algorithms have been developed. BQE is one of the most well-known one. But these algorithms still have challenges, and they do not go beyond classical computation. In order to exceed the classical ones, we need tens of qubits computations. However, using the tens of qubits, then quite quickly computation will become impossible. And also, exponentially, there may be advantage going beyond classical computing, but it's not clear. That's why breakthrough hasn't been achieved. But in the future, FTQC, if that's realized, then for sure there will be exponential advantage. That's theoretically proven. So if that's achieved, there will be a breakthrough. However, the time is pressing. FTQC, if it takes 10 years, 15 years, that's a current estimate for that to take place. But in order to achieve the breakthrough in more short time, then how to fill the gap of what we can do today? For instance, error mitigation, error correction technology has to be developed, and in the near future, in 4 or 5 years, on devices, FTQC algorithm should be running. Then it will be leading to a quick breakthrough. That's all. Thank you.
Thank you, and I fully agree with you. Fault tolerance, with NISQ, it is very important to mitigate the noise. And Ohgoe-san, from your perspective, could you share your thoughts? Yes, kindly overlapping with Mr. Gao, but the immediate challenge is how we can survive and thrive on NISQ. VQA is the most famous algorithm, but with VQE, as hardware scales up, can we scale up applications as well? Actually, not. There is a big hurdle to overcome. In my recent joint research, I am now working on actual machine, and you directly feel that way. So I think a kind of paradigm shift is necessary. It will be a quantum classical hybrid algorithm still. However, quantum computing will cover what it is good at, and the classical computer will handle what it is good at. And I think specifically there are many ways to do that. Last year, Google published a Nature paper, and the quantum Monte Carlo and the hybrid approach was proposed in that paper. This combination, and that was a new insight about a possible combination of quantum and classical. So for us to survive NISQ, it will not only VQE, but there could be various better ways to combine a quantum and classical, and I hope that a good applications will be developed. So yes, eventually we will need FTQC, but in the meantime, we will have to combine the power of quantum and classical, take advantage of the respective strengths. Thank you very much. So yes, we have to work on algorithms, and hardware also has to mature. So for the several years to come, earlier you said that FTQC takes 10 to 15 years, but we cannot wait that long. Your managers may tell you so. We cannot wait that long. So in the several years to come, what kind of outcome do you expect? What kind of expectations do you have for the 4 to 5 years to come? Ishii-san, please.
Yes. VQE, we mentioned VQE a lot. When we started to work on quantum computing, VQE was the thing we had highest expectations. That said, VQE might not be that easy. I think people are openly talking about some difficulties and challenges with VQE. So if we pursue VQE and work on it very hard, there might not be a major breakthrough in several years' time. It could be because you cannot tell what happens to a research, but it is unlikely that it will turn out in a great manner in several years. And Mr. Gao talked about hybrid algorithms earlier, and we did have good researchers on hybrid algorithms, and those algorithms have possibility to resolve the existing challenges in a few years' time. Some time ago, Q2B23 published a paper about QSCI, and today someone talked about the quantum Monte Carlo. Those could be options for us as well. And on the other hand, IBM published a roadmap. When I first heard about it, I was kind of suspicious whether it is realistic or not, but it showed that if a giant company concentrates their resource onto a topic of their choice, then it proved that it can do so much. So I think that in the framework of NISQ device, those problems could be solved. But in this shorter time frame, I think ANIDA might have a bigger potential. Thank you very much. Gradually, one by one, the new possibilities will fold out. Ohnishi-san, what about you? I would like to know any promising algorithms which could turn out in several years. But if you think about the learning from the quantum advantage proved and the random circuit algorithm, the Google showed the areas where quantum computing is better than classical computing. And instead of doing it randomly, the probability distribution needs to be provided, which is necessary in chemical or physical area, and then it can be processed by chemical computing to extract useful information. QSCI, quantum sampling CI. I think QSCI is one of the future ways for us. So something that cannot be created by classical computing, but the distribution can be easily done by quantum computing, and the distribution will not be random, but it is similar to a problem in physical or chemical domain. I have no idea what we can do that, but I hope that collectively we can come up with a good idea. So that was about algorithm side. And speaking about hardware side, in the near future, the different approaches will explore their different applications. For example, the superconducting processor has advantage of a more number of qubits, and a trapped ion has an advantage of high fidelity. So they don't need many quantum circuits, but they can maybe run certain algorithms taking advantage of the high fidelity and the optical. But just like Xanadu, the quantum advantage beta Gaussian sampling, that could be also put to industrial use.
this is the direction I foresee for each of those technologies. Okay, and if there are great algorithms coming out, then please let me know. I really want to know. There are 5 minutes to go, but we like to take questions from the audience as well, if you have any. If you have a question, please raise your hand. If not, actually, I have more questions to ask from myself. Okay, later I will ask the audience again. So earlier we talked about it takes teamwork of different computers. We have supercomputer or maybe annealing for optimization problems, but there are certain problems that only gate computers can solve. So there are pros and cons and nothing perfect. That is how I want to summarize your comments. But maybe in 2050 or 2060 or 2040, when the quantum technology matures to some extent, then what would be the end state that we can foresee in terms of the roles played by different technologies? Before I joined JSR, I was at Kobe University, and Kobe University had the K computer, and I was writing quantum programs for the K computer. So I was involved in HPC programming. And based on that experience and what I see today and how the technology is evolving, back then, when I was working on HPC programming, I was really tired of this cumbersome programming process. Whenever I write some calculation, I have to see how computers are connected to each other, and always I have to think about how to reduce the computation cost by changing the routing within the processors. But when you're using smartphones, you never think about how hardware is linked to each other. You are just getting information. So from a user's point of view, as long as you can get the result you want, you would never care about the backend. For example, in terms of quantum chemical computing, you send a request to solve a problem. Then, okay, this problem is easy, so let's route it to classical computer. And you can solve that problem with a cheaper laptop. And if it requires supercomputing, then it is sent to supercomputer. And then if it requires quantum computing, it is sent to quantum computer. So in this kind of manner, if the technology evolves in this way, I would be really happy. IBM is working on quantum-centric supercomputer or quantum-centric data center. And I think this is the idea for hiding the backend from the end user point of view.
Yes, I have been thinking about the questions, not thinking about the hardware, but we need to consider interface, and that may lead to a big business case. I think we can entertain some short questions, one or two. Are there any? Thank you. In the past several years, like 3 years, 5 years, joint researches and the verifications that you have been carrying out. And at the time that you exceeded quantum, looking back from that timing, in the past 5 years, let's say, do you feel specific changes? For instance, it's better to enhance the disks, or regarding FTQC, it's better to sophisticate the countermeasures. So is there changes in your thinking about this approach? In my case, I started in 2018, and back then, I used the Wiki UE and putting it in the quantum computing, then we'll be able to get some answer. But actually, when we did that, the VQE has some challenges. And also what I felt strongly is that there are errors with actual machines, and that's quite difficult to control. So we need to eliminate the noises from the actual machines, and we need to extract useful information, but that's quite challenging. Therefore, error mitigation or error correction. Well, I think for those, quantum computing has the strengths. And if that's achieved, then there will be a big change in the space of quantum computing. That's something that I understood quite sharply in the past several years. And that has to be combined with algorithms, and that will be leading to the practical use. Thank you. It is almost a time to close the session, but last question I'd like to ask you. So there are expectations, but at the same time, it is considered to take some time. And it's going to be also a global competition. And we need to keep a community active, and not just materials, but there have been various different communities of quantum. What's your expectations to the community activities? Kotsan, please. What I expect to the community is, let's see, the American communities, I think, is quite successful, especially Q Network by IBM. IBM in the center, and academia, universities, and business corporations, they have been involved, and they have been actually building use cases. So the industry, academia, and the governments, they have been making consolidated efforts and producing good results. Therefore, in Japan, we need to have the same mechanisms amongst the industry, academia, and the government in Japan, so that we'll be able to build a good community. Yes, we would like to actually build a strong community. Yes, Ishii-san, yes. So, community is very important. The technology is not complete. And you may consider that we will invest after confirming the technology completion. However, if that's the case, you may miss the opportunity. Information is very important. And for each individual company, there is a limitation for information to obtain. Therefore, in that sense, I think community will play a great role. In the community in Japan, we have a QPAC. And the beauty of QPAC is that you'll be able to choose how deeply you'd like to be involved. You can just casually participate, or you may focus on a certain algorithm and you may be deeply involved. So I think in that sense, the needs of each individual company will be satisfied. In quantum computing, there are some specialists working on this for 20 years, 30 years, and also there are some fresh people just started working in this space. So I think depending upon the needs, it has provided the activities. Yes, in order to keep the momentum of quantum computing, as the catchphrase says, I think a roadmap has to be shown. In the case of hardware, the roadmap often presented. However, applications or technique or methodology development, roadmap needs to be shared, and you will also demonstrate that steady progress has been made. And that's quite important for the society or community to understand it. Therefore, and that's difficult for each individual company to do so. So as a whole, entire community, that has to be demonstrated. In the semiconductor, roadmap is quite solid, and the current situation has been achieved, and so current computation system has been established. So the same thing has to be applied in the quantum system. Ohnishi-san, please. Yes, I do share the same expectation for the community, and also when there is a community, I think it is quite beneficial, because you'll be able to know such and such companies are seriously tackling with quantum computing, especially for young people like junior high or high school students. These people, students, will be encouraged, knowing that the specific companies are involved in the communities, and they will be encouraged to participate in the space. Thank you very much. So there are expectations, but also there are lots of challenges. There are risks, and also the actual machines are also challenged. That's also mentioned. So it's still a young industry, but as McKinsey, we have been also have a perspective, and at a certain threshold, when it's achieved and going beyond that threshold, then there will be the jump. So Amazon's gets coming in, and then there was a great leap actually mentioned in the semiconductor area. Brothers Light in 1903, only 120 feet, 36 meters of a flight became possible. But in the World War I, the total Europe has been a battlefield, and it's only 14 years since the Brothers Light made a first flight. But there was a big leap of technological development of airplane. So in the short run, I think there was a great innovation, and probably in the next 10 years there will be exponential technological advancement. And once the U.S. comes in, there is a capital power, and actually, in some areas activities are so passionate in the U.S., EU, but not in Japan. Sometimes that's observed, but I think we need to generate lots of use cases thinking about the industrial development of Japan in quantum computing. So we had 40 minutes, but we could have very productive discussion. Thank you very much.